context, and very few papers actually put things this explicitly into this context, you can go for quite a while without really understanding what's going on, and without really understanding the point of a question, because the question only makes sense if you know what the models are, and there's different ones. There's evolutionary models, there's biochemical, physical, and so on and so on. And let me show you one thing that happens when you don't take care and appreciate this during education. So this is the map of the solar system that French schools use to teach children about the planets, okay? And there's other kinds of models, okay? So this is a thing, not to scale, obviously. That would take, never mind, farther than Boston. How many of you can go out at night? You all learned the solar system in grade school, right? How many of you can go out at night and in 3 seconds find all the visible planets in the sky?
Give me 5 seconds.
5 seconds, that's pretty good.
You could.
Okay, anybody else?
Alyssa could.
Yeah.
So,
But it depends on the time of year, which ones you can see.
it depends which ones you can see, yeah, but if all the visible ones that are out that night, you should be able to find them really fast. And if you understood this model, you would know how to do it, okay? And what happens is, now we need to build a solar system here. We have the sun in the middle, and then we have some planets that go around it, and let's put in a moon here. Let's make my coffee cup. There's more. I'm not going to show them all, but there's Mercury, Venus, the Earth, Mars, and so on and so on. So the first thing you have to know in this model is that all of the planets that are visible orbit the sun in a plane, almost a very good plane, okay? There's not one that goes like this. They're all running around on the table, okay? And the second thing is that the Earth's axis rotates it around an axis that's perpendicular to this plane, okay? That means that from a place on the Earth, if you're looking at the sky, you just have to find that one plane running through the sky where all the planets are, and all the planets will be there. And you all know one thing that's on that plane, the sun. So if you know where the sun rises and sets here, and the path it takes across the sky roughly, you'll see all the planets on that line. Wow, isn't that cool? I mean, that's useful knowledge if you've learned this model. But what the teachers forgot was that when they taught you all the pieces of the system, they didn't show you how they were interconnected in a certain way. And there's other puzzles that you can pose with this model. So for example, you know that the moon rises and sets like the sun, right? And how long does that take? Is it a day? Is it less than a day? Is it more than a day?
28 cycles.
Well, it goes in 28-day cycles. That means if you have to divide 28 by 24 and you get 1 point, right? So it's a little more than a day. So if you're on the Earth watching the moon, it rises and sets. It takes a little more than a day to go all the way around. If you were standing on the moon and looking at the Earth, how long would it take to rise and set? Ha!
Forever.
Never. It would either be, it's always in the same place in the sky, because the moon, as it goes around the Earth, its face always stays, right? If you were standing on the moon and looking at the sun, how long would it take the sun to rise and set? Okay, anyway, 28 days. Anyway, figure it out. But if you knew how this model worked, you could put your mind into any position in the system and look at it and discover interesting things and important things. The same thing is true of our scientific models. So this is what I call thinking like a molecule. That means putting yourself into the position of one player in a system and looking at the whole system from different perspectives, okay? So, but we don't teach this. We forget this. And we forget that a study or a question is actually thinking like a molecule often. It's looking at a system from one perspective, but first of all, you have to know what system you're in. Am I in the solar system or a cell? It's kind of relevant. Okay, so this so often remains hidden, and also the goal remains hidden, that I'm not trying to just give you a bunch of sentences or facts to repeat, but I want to show you how the system works so that you can reproduce it. If you have this in your mind, you can reproduce it in all kinds of different ways later. And what's really interesting about this is that if you look at this, so these are scientific words: transcribe, we also say read, we talk about transcription, promoter. Those are all metaphorical words, okay? And there's a sort of guiding metaphor behind it, which has to do with reading and writing. So let's rewrite this as a metaphor. You have a machine, that binds to, that reads, that transcribes, that understands a text, and it usually does this in a directional, so a text is linear, so that makes it linear, directional. And what we've changed in the story is to say the machine can read and make sense in both directions. So we've taken this pattern from a scientific model, and we've translated it into a metaphorical model. And that's okay, because remember, the things in your head are not real things. You don't have SRY in your head. You have a pattern, a concept, a little pattern of ideas that are linked to each other. And that's what you're playing with in your mind. So this is allowed, and it's also the basis of models. What happens if we take this now and rewrite the text? Here's my proposal. You can do it 100 ways. So our DNA can be read backwards and forwards. Our cells constantly respond to changes and challenges to survive. They manage this by drawing on different sets of information in their DNA, then using it to produce other types of molecules. The process begins when a cellular machine locates the recipe for a molecule it needs in the vast DNA library. The machine attaches itself, reads the information there, and transcribes it letter by letter into an RNA molecule. Until now, scientists have thought that the recipes only made sense when read in one direction, like this text. But scientists at EMBL have now found that when the machine binds to DNA, it can read and transcribe in both directions, sorry about that, starting from the same point. The first hint that this could happen came when the team found RNAs spelled forward and backwards starting from the same point. They went searching for other molecules that followed this pattern and found it's a very widespread phenomenon, not only in human cells, but probably in species of animals and other organisms. There are many implications. First, it tells us that many species' genomes contain, and so on and so on and so on. I did this in 10 minutes last night because I knew how to do it. And I think that any person who reads this, not only will they get the story, but they can even pose a couple of very interesting scientifically relevant questions. So can you think of one? If that's how this thing works, what's sort of the big question that you would ask?
What controls which direction it reads?
Exactly. What controls? How does it know which way to read?
What do the backward reads do?
What do the backward reads do? And you can do that without knowing anything about science. This means that taking this metaphorical approach, understanding that your knowledge is organized in patterns, recognizing those patterns helps you communicate, helps a lot more people understand what you're saying, but also helps you ask a scientific question that maybe you wouldn't even have thought of. So I'll give you another example. On the back, I've drawn another diagram on the right side. Now I cannot see it all this, but there's a letter A, and the letter A represents a little nuclei of neurons that are extending processes out to point B. The axons reach. And so if A is stimulated, it sends a message to the neurons in location B. But some of the axons double back. I think I labeled that C, didn't I? And they go back to the original population and they stimulate the original. And then from point C, that signal goes on to other places. Now, a student was writing a paper in which they asked themselves the following question. Is the feedback from A back to A, does it have any influence on the signal that arrives at B? So they found this really cool way of interrupting only those axons going back. And then they measured various outputs. They stimulated cells at A and measured various outputs at B, B, sorry, my glasses. And the student, at the end of a writing course, we always do the exercise, okay, how are you going to explain this to your grandmother? And she started by trying to list brain regions and different layers of, whatever. And instead I said, find a metaphor. So we looked for a while and we finally found one, and that was, imagine a singer. Sometimes they record their voices in a sound studio and they have headphones on that actually completely block their own ability to hear their voice. So the question is if you had such headphones on and you were singing, would it change at all the quality of if you couldn't hear yourself sing, would it change the result? And obviously it would, right? So that was an interesting metaphor to use, or maybe it wouldn't in this case. If you use that metaphor, then we've changed the idea of a signal transmission from neuroelectrical charges to sound. So then you could play with this idea in a few other ways. You could say, well, what are some other ways that I could stop a sound from getting back to its source? You could make the background noisier, or there's all kinds of things. If you were in a bar, you know, trying to pick up somebody or whatever you want to do, maybe that's not politically correct here, I don't know. Anyway, how could you stop yourself from hearing yourself? Well, if the music's too loud or so on. And all of those ideas, if you translate that back into the brain, you can find correlates. So maybe there are other cells that are interfering somehow with the signal because they're making noise. And there are other questions you can ask that she hadn't even thought of really using the system, and that is, maybe this is a regulatory system. Maybe the cell can tweak the amount of feedback that comes back. And you should then not only measure what happens at point B, but you should measure whether the person who got the information or heard the music can tell somebody else how good it was or what you said. And then you would go out to the innervation points of those target neurons and test what happens there. And she hadn't even thought of that because she hadn't arranged the information that way in her mind.